So it's a delight to be here. Thank you for the invitation, Nicola. So I'm giving a lecture tomorrow in the chemistry department where I will probably give more of an overview of the sorts of thing we're doing and the big issues in the field. But today I wanted to try and tell you a little bit about some of our work where we've been trying to link experiment with theory. And so I'm not a theorist, so you have to go easy on me. But what I wanted to do was to try and highlight some of the challenges we've had and maybe to sort of provoke some conversations and discussions. So do feel free to just interrupt if you'd like. And I'll try not to walk around too much for the camera. So just to sort of briefly spend a few minutes on the context, we're interested in materials for reducing CO2, and particularly if you're trying to get more renewables into the grids, then you've got to work on materials that can both store electrical energy and also can convert to chemical energy. And so batteries, as you will see, play an important role. So do fuel cells, particularly in converting chemical energy into electrical energy. And then, of course, in transport, again, batteries play a role in CO2 emissions by increased efficient uses of fuels. So what is a battery? It's 25 years since the rocking chair battery was discovered, and just to sort of remind people in the audience that these are complex material systems where you've got to put together materials you've got to get lithiums. If it's a lithium-ion battery, you've got lithiums in and out, you've got to get the electrons in and out, and you've got to hold this together for multiple cycles, which for batteries, for portable electronics, could be for a couple of years. But if you're trying to make a battery for the grid, then you're looking at systems that are going to have to work for 20 to 40 years to be compatible with grid industries. So I just wanted to sort of talk a little bit about some of the new areas that are out there, because it's really sort of an exciting space for materials chemists and material scientists and engineers and physicists, because there are a lot of interesting problems to look at. And so for the grid, the areas that I want to talk about today are sodium batteries, so where we're replacing lithium by sodium because it's cheaper, and also because you can get rid of the copper current collector, because sodium doesn't react with aluminium, unlike lithium. Redox flow batteries, sort of ideas of very big batteries that I won't touch on today. And then in transport, people are looking at things like magnesium batteries, all solid-state batteries, and lithium air. Okay, so I'm an NMR spectroscopist primarily. That's at least my background, although I'm also a solid-state chemist. And so one of the nice things for us is that we've spent a lot of time trying to push the use of spectroscopy, particularly the lithium NMR, in this field to see what sort of information we can get out of it. And this is the sort of normal slide that the battery chemists would give in terms of lithium, sodium, and magnesium, comparing the costs of the resources. And this is my slide where I show you the different NMR active nuclei. And for us, the interest is sodium is 100% abundant. Magnesium is a low abundance, but and also very low sensitivity, so it's going to be a challenge. So what I want to do in this talk is to give you 4 stories, and possibly a 5th if I have time, on how we're combining structure, prediction from theory to theoretical calculations to experiments in anode materials for lithium and sodium batteries. I want to tell you a story that's really theory-driven on looking at structural transformations, then one on doing hyperfine shift calculations to understand the lithium NMR and the sodium NMR of battery materials, and then finally end up with where we are on looking at fuel cell materials, and particularly the electrodes for fuel cells, for solid oxide fuel cells. So the story started a long time ago, or at least now it's sort of almost 10 years ago, when I started to look at replacements for lithium-ion batteries to replace graphite. So if you move from graphite through to germanium and silicon, you can get an increase of capacity by about a factor of 10. And so there's been a lot of work over the last few years to try and push the use of silicon for this application. And I can go through and answer some of the problems about some of the issues there, but today I want to think more about the structural chemistries associated with it. And so this is a typical plot of cycling a lithium battery versus silicon. So you start with crystalline silicon, you react, it forms an amorphous lithium silicide. When you go all the way through to the N-member phase, Li15Si4, it reforms a crystalline phase. It goes back with a very large overpotential, which is bad news in terms of the battery, to form an amorphous silicon phase. Goes back with two processes, and depending on whether you go down to low voltages, you can go back almost reversibly, or if you go down to 0 volts, then you go back with this overpotential. So just by looking at one of these plots, as an electrochemist, you can just see how rich structurally some of the processes that you have to try and understand in these systems are. And the problem that we have is that most of these chemistries are amorphous. And so the sort of traditional methods that one would use, like X-ray diffraction, and that's shown here, just don't work very well. So you've got your crystalline silicon forming this N-member phase Li15Si4, but for most of the electrochemical discharge, you can see there's just an amorphous component. And so that's where lithium NMR comes in. So what we tend to do throughout a lot of this work is to step back and look at the phase diagrams and work out what the thermodynamic phases are to guide our interpretation of the types of structures that one might expect. And if you do the reaction of lithium plus silicon at 400 degrees centigrade, you can walk through a whole series of different lithium silicides. But at room temperature, as I mentioned, you actually miss out these crystalline phases, and instead you go to this metastable phase Li15Si4. And so we're sort of interested as battery chemists to try and understand, what's stopping us going through the crystalline phases rather than and accessing instead these amorphous components. So the first thing that we do to understand the system is just to make all these different silicides and study them by lithium NMR. And so this is lithium-7. It's a so-called quadrupolar nucleus, spin 3/2, and it's very sensitive. And then what you do then is to acquire the lithium NMR spectra of these materials, and then you can use them as fingerprints, so that when you look at the batteries, you can see whether similar compounds have been formed. And in terms of the theory of these materials, it's actually quite difficult. And so to date, we've still not been able to do a very simple thing of to try and do chemical shift calculations of these materials, because they're semiconductors and almost metallic. And so at the moment, all we can do is to use qualitative arguments to try and rationalize these shifts. This shift here at negative frequencies is actually because this compound, as I'll show you in a second, contains 5-membered rings. And so it's the lithium sitting between two aromatic rings that's giving you that negative shift. But basically, there's a trend that if you have lithium near clusters, whether they're these 5-membered rings or these dumbbells, you have shifts that are about 20 ppm. And as you move to more isolated silicons, you get a shift to more 0 ppm. And so the environment for Li15Si4 sits at about 6 ppm. So what we do is we take these model compounds, and then we contrast them to the NMR spectra that we get when we discharge the battery. And so what this is the electrochemical profile, and each of these red dots corresponds to a place where we stopped on the electrochemical profile and have pulled the battery apart and do NMR. And the purpose of this slide is just to illustrate something that's very interesting about this system, is that because the silicon bonds are so strong, it's kinetically very difficult to go through and reorder the bonds to form the different kinetic phases, because that would involve you going from a diamond-type silicon structure to form these 5-membered rings and 3-membered rings, and instead you operate and you form these sort of amorphous phases that can still contain these dumbbell-type structures, and then as you push through to lower voltages, you break the dumbbells apart and you form the compounds of isolated silicon. But because you're operating at an overpotential, because of the difficulty of breaking the silicon-silicon bonds, you also access environments from lithium near isolated silicons, which you shouldn't get until you're more lithiated, because you're operating at this higher overpotential, you've got the extra energy to go and do that. It's easier once you've formed a dumbbell to break that apart than it is to break the crystalline silicon apart. Okay, so that was sort of a preamble for my story that I really wanted to tell you about, and that was the moving from the silicon chemistry to the germanium chemistry. Now, germanium is not necessarily going to make a great battery material because it's too expensive, But on the other hand, you've got higher lithium transport in germanium, higher electronic conductivity. So it actually is a better material than the silicon. It's also a material where the lithium again reacts with, the germanium reacts with lithium again to form the same M-membered phase Li15 germanium 4, but it goes through a whole series of materials that are either crystalline, amorphous, or partially crystalline. And there have been a whole series of proposals as to what's formed in the structure in this phase diagram. And so what we did to make progress in this area was to team up with Andrew Morris and Chris Picard, who'd been developing these ab initio random structure searching methods that they call AIRS to try and obtain the different crystalline structures as a function of lithium-germanium ratio. So you can see as you go from all germanium through to lithium, it's an extremely rich phase diagram. And so what they do is they identify lots of different compounds, they rank the energies, and then we determine the so-called convex hull. And if you connect the points from one to the other, you can work out which compounds should form as you lithiate. But you can also see that there are a whole series of compounds that lie just above the convex hull, so they may form in a battery. So with these predictions, we then went off and we made some of these compounds. And specifically, something that I hadn't really brought your attention to was that the phase Li9 germanium 4 was the one that was predicted by people in the literature to form halfway through the lithiation process. So going back to here, this was a phase that was proposed by a number of authors. But when we looked at the convex hull, the Li9 germanium 4 phase wasn't stable. Instead, this phase Li7 germanium 3 was. And when we tried to make Li9 germanium 4, what we actually got was Li7 germanium 3. And so consistent with the theoretical predictions, this seemed to be the stable phase. And this is just showing you a comparison of the diffraction, where we fit the diffraction pattern first of all with the Li9 phase, and it doesn't do a good job, but it does with the Li7 germanium 3. So then we obtain the NMR spectra of these materials, and the NMR spectra, again it's lithium, are very similar to those that you saw already for the silicon, which is why I showed them to you. So in the compounds where the lithium is next to now germanium dumbbells, you get this large positive shift. When you go to the compounds where you start breaking the dumbbells up to have dumbbells and isolated germaniums, it shifts to lower frequencies. And then when you have this 15-4 phase, you actually have a negative shift due to isolated lithium near isolated germanium. Moving to the 22 germanium 5 material, this is now a metallic phase, so these are all semiconductors. So you now have a shift in the opposite direction due to the so-called night shift. And the night shift is a measure of the density of states at the Fermi level as probed by lithium. So these NMR spectra contain information both on the sort of local structures of the germanium and the bonding of the germanium, but also on the nature of the conductivity in the systems. So we then go ahead and we do exactly the same thing. We make lots of batteries, we stop them at different places, and we can do diffraction on them. And so here's the germanium. As you lithiate it, you can see a new phase forms. That new phase has the peak positions corresponding to the phase that was predicted out from the AIRS method. The Li7 germanium 4 phase is there. And then you get a region further on where the diffraction becomes not completely disordered. You can still see some Bragg reflections, but there's not readily indexed to any known structure type. So you can do the NMR of these different materials. The NMR is consistent with the ex situ our model compounds. There's the NMR shift of Li7 germanium 3. As you move down, we get the next phase, Li7 germanium 2, and then eventually we get the Li15 germanium 4 phases. So something I haven't talked about, and something that I will talk about tomorrow in my lecture, is what my group has done over the last few years is really push the development of in situ methods or operando methods to look at batteries while they're being cycled. And we do that because we're interested in trying to capture metastable phases or phases that don't survive if you were to take the battery apart. And so what you're looking at now is an in situ lithium NMR spectrum of the battery as it's being discharged. So here's the electrochemical profile, and here's the NMR spectra as a function of discharge. And what you see that's very interesting, and in contrast to the ex situ study, is that you start to first of all form this Li7 germanium phase, but you don't see a series of discrete environments as you go from Li7 to the Li7 germanium 4 to the Li7 germanium 2, or these two environments that I just said here, so Li7 germanium 3 to Li7 germanium 2. Instead of having the discrete peaks that you see in the ex situ, you see a continuum as you lithiate. And so what's going on can be readily explained by, again, looking at the different phases that we identified in the Ayres calculations. So as you go from the 7.3 to the 7.2 phase, you have this whole plethora of different phases that contain dumbbells spaced by increasingly more lithium ions, and then eventually dumbbells with isolated germaniums. And so when you're lithiating these phases at room temperature, the system A can't decide between all of these different phases, and B, the kinetics are too slow for the rearrangements, that it basically just goes through this poorly crystalline region where it's just a mixture of all of them, till it finally gets to a phase where essentially all of the germaniums are isolated, and only then can it nucleate the crystalline phase. And so it's sort of a nice illustration of the fact that in systems where you've got multiple phases that are present with similar energies, and the kinetics are slow for structural rearrangements, then the system just goes through and can't resolve itself, and you get these amorphous and poorly crystalline structures until you're in an environment where you've got isolated germaniums, the lithium ions are relatively mobile in the system, and then you can nucleate and grow a crystalline phase. Okay, so we've done similar things with tin anodes that I won't really go into in great detail now, but for sodium-ion batteries, there's no good battery anode material. So sodium can't intercalate into graphite. So lithium intercalates into graphite, potassium intercalates into graphite. If you try and intercalate sodium into graphite, you plate sodium instead. And so there's a push to develop alternative anode materials for sodium. So the best materials out there are these things called hard carbons, which are disordered carbons, but they have lower capacities than graphite. And so tin does a good job, although it's got problems associated with breakdown of electrolytes. And but you can see it's got very high capacities that are almost more than 3 times that of a hard carbon. Structurally, it's a mess at the moment, and there's a lot of different phases that are proposed. So again, using these Ayres methods, we were able to identify what some of the phases are in this phase diagram, and in particular, look at regions where we had an amorphous and poorly crystalline phases. And so what we did was, starting with some of the structures that we'd identified from the Ayres method, was to start to do MD simulations with these as input, and then we did reverse Monte Carlo fits now of this is a pairwise PDF, a pairwise distribution function analysis of this amorphous phase, which we could then fit to pull out the different components in the structure, and contrast that with our NMR. Now we're doing tin NMR, and we can then, by looking at the tin NMR of these systems, identify the types of motifs that are present in our amorphous phases. So just to sort of summarize this section, I hope I've shown you that by using a combination of NMR, other methods for looking at local structure that I've touched on less, but we use very routinely, the pair distribution functional analysis of total scattering data, along with DFT, is really a good way to look at these poorly crystalline and amorphous materials. Okay, so I want to talk and change gears slightly, and this is now a theoretical study done in collaboration with my colleague in Cambridge, David Wales, where we're looking at how structures rearrange. And one of the biggest challenges in layered cathode materials and in oxide materials in general is that after multiple cycles, structures change, you can lose oxygen, you can have migrations of cations, and that can be a mechanism for battery failure. And so the material that I want to look at is the transformation of a layered phase lithium manganese oxide on cycling. And in the nickel doped variants of this is, for example, responsible for the gradual voltage drop in these materials. You get transformations of things like layered to spinel transformations, which again have significant negative impacts on long-term stability. So the challenge we have is, how do we look at these structural migrations and changes that involve very large systems? And something that we don't have a solution for, but we've just started to think about how we might do this with these combined hybrid eigenvector following approaches that David Wales has pushed. So this material has been well studied by Gerd Sader and his group a number of years ago, and I'll just walk you through some of it. So I'm going to look at this layered lithium manganese oxide. The problem with this material is that it's metastable. So it's the direct structural analogue of lithium cobalt oxide, which is the major component of most batteries, although some of them being replaced by materials where you're substituting some of the cobalt by nickel and manganese. But unlike lithium cobalt oxide, it's got a monoclinic distortion coming from the fact that manganese 3+ is a D4 Jahn-Teller ion. Because this material is metastable, you make it via the sodium form and you ion exchange to make lithium. But if you pull 50% of the lithium out, it's metastable with respect to transformation to the spinel. And so that's the transformation that gradually occurs as you cycle. And so Anton van der Ven, when he was in Gerd Sader's group many years ago, looked at this mechanism of how this might happen. And what we wanted to do was to go back and look at this in more detail, to look at the concerted processes by which this would occur. So this is just the electrochemical signatures of how this happens. If you pull lithium out of the structure, what you gradually see is you move from the sort of electrochemical profiles that you expect for the layered material to that you would expect of a spinel phase, where you've got the high volt process at about 4 volts, and then you've got involving tetrahedral sites, and this is the electrochemical signature of the octahedral environment. And so what you get is sort of a layered phase that then has, this was proposed by Gerd and Anton a number of years ago, where you have a sort of a dumbbell formation of lithium in the tetrahedral sites and manganese in the tetrahedral sites, which then eventually will transform to the spinel. So what we're going to do is to use this approach of David Wales. I don't really want to go into the details of how you do this to a theory audience, but I'll just sort of walk you through the hybrid eigenvector approach. Basically, what we do is we approximate the potential energy as a quadratic, and the reason why this method is efficient is that we only need to determine the smallest eigenvalue, an eigenvector, to follow the transition from one structure to another. And what's nice about it, unlike a method like the nudged elastic band approach, is we don't need to know the trajectory over which the ion moves, and we don't need to know the beginning states and the end states. We can just set it going and see what happens and look at the cooperativity of the different transitions. So just to sort of walk you through it, one of the problems is, so David had previously used this method and coupled it with semi-empirical approaches, but we can't do this for these battery materials because the processes by which they rearrange are intrinsically coupled with the electronic structure. And Gerd, for example, had shown that if you start off with a mixed manganese 3, manganese 4 compound, then you even get disproportionation of some of the manganese that was responsible for lowering the transition state. And so you can't just couple it with a semi-empirical approach. You've got to use DFT, which inherently becomes very expensive. And so what we have to do is sort of start the calculation off in a starting configuration where things are likely to happen. And on the basis of the fact that the Li 0.5 MnO2 is the compound that's the most metastable with respect to transformation to the spinel, that seemed like a reasonable starting point. Now this material has a configuration or an arrangement that's ordered, that's lowest in energy, and it is that because it's the environment where you get a sort of coupled Jahn-Teller distortion, where you orient the Jahn-Teller distortion with the manganese and the DZ squared orbital couples, and there's a preferable manganese oxygen lithium arrangement. So that's our starting point. And then what we do is we let the sort of the eigenvector following approach go, and then it does its thing with us actually having to tell it what to do. And of course that depends on whether the computer will do it. And so you can see the first thing is that the ion jumps from that position to there. And that's not exactly desperately exciting, but you can get to see it again just to sort of wake you all up. But then what we can do is we can analyze the energetics of the processes as it moves through the along the different trajectories, and we can identify the transition states and the intermediates. And the sort of take home from this particular section is that this tetrahedral site, as it goes from octahedral through the window, is a local minimum in that pathway. And then what this allows you to do also is, and just so I run it again, is you can start to look at how you get coupled processes. So if you watch carefully, sorry. You can see the movement of the manganese as it's doing it, but it's more obvious in the next one, so I'll move on to the next one. So the next process then is you're in this environment here, and you've got to now move. So here's the octahedral site, and a good day will do something. So then that's the movement to form the tetrahedral site, which then pushes that manganese out. And so again, you see that. And the advantage of this approach is that you don't have to a priori know how the movement of the different ions is coupled with that process, which if you'd done some form of nudged elastic band method, you'd have to provided more of that information. Then the other thing that you can do when I actually get out of this mode is to again think about what's going on in this. And again, you've got your octahedral minimum. You then move into the transition state across over the tetrahedral lithium sits on top of a manganese, and then that pushes down the manganese there, going via a 5-coordinate environment. And you can analyze the oxidation states of the manganese throughout. And what you find is it's manganese 3+, but when it gets down into the final configuration, you get a disproportionation, so that the manganese that then sits in this tetrahedral site is actually manganese 2+, and you form manganese 4+ in the layer here. And so that then is something that stabilizes this dumbbell configuration. So just to look at that in more detail, you start off with these sort of Jahn-Teller manganese 3 ions, you go to form a square pyramidal structure, and then when it goes to the tetrahedral site, you actually end up forming a manganese 2+ environment. So why is this important? It then starts to allow you to ask questions like, how could we stop this process happening? And what people have done in the literature is to try and put in dopants or substitution ions into this layer to try and stop this process. And one of the, so they basically put in every single cation that they can think of that will go into this structure. And the one that's sort of universally always used is aluminium. And that has some effect in slowing down this structural transformation. And so once you sort of identified the ways by which you get these structural transformations, you can then start asking, well, what happens if you then, or what happens to the transition states and the energies if you put in these substitutions? And by doing that, we were able to show that aluminium is probably the only one that makes a difference to the activation barrier of this process, but only if it's sitting in the first coordination shell of the manganese that actually moves. And so the sort of consequence of that is you have to have extremely high concentrations of aluminium before you can even make any impact on this structural transformation. So I just thought I would just give you some intermediate conclusions on this, that we can use these types of methods to interrogate mechanisms of how you get structural rearrangements and how they're coupled, and the electronic structures that occur on the way, which is all very interesting, but we still have significant challenges that hopefully there are people in this audience who would be better equipped to address, that we really do need to address in battery materials. And one of our problems at the moment is, we can't change composition. So we can't ask the question, what happens if I pull a lithium out, unless you set up cells where you've sort of artificially put lithium in one place and you still maintain the fixed composition in the cell. The way the calculations are set up, we can't change the cell size and the volume, which means, again, if you've got structural transformations, it's not clear that you capture the transformation fully. And so this, I think, is one of the sort of biggest theoretical challenges we have in looking at battery materials, is how do we look at the structural transformations that occur in the short term, but also over long terms, that involve very large rearrangements. And you can do these often by semi-empirical methods, but it's not so straightforward to do it with DFT-based approaches. Okay, I'm going to change gears now and tell you a little bit now about our work on calculating hyperfine shifts in sodium-ion materials. So sodium is never going to beat lithium in terms of energy density on a gravimetric basis, but if you start looking at the capacity on a volumetric basis, and sometimes you're as interested in the volumetric energy density, then you can find sodium materials that are competitive with some of the sort of lithium ion favorites like lithium iron phosphate and lithium manganese oxide. And so there's a whole series of layered phases that have been made that are reasonable, and they cycle well. And there's a British company, Faradion, that now has a battery based on a layered sodium nickel manganate and a hard carbon as the anode. And one thing that came out of these studies was that if you look back in the sort of 25 years ago, before the development of the lithium-ion battery, there was as much work going on on lithium-layered materials as sodium-layered materials. The lithium-ion battery was invented, pretty much the whole field was shut down, and then we all started to believe that sodium ions, because they were bigger, really wouldn't diffuse all that fast, and so you'd have problems of rate. But actually, when people went back and looked at it, it was clear that in these layered materials, because the sodium's larger, the layers are propped apart, and you can actually have some very high rate behavior of these layered type structures. But the structural issues are slightly different. You get, because the layers are propped apart further, you get more structural rearrangements involving shearing that you've got to get rid of. And you also have a whole series of orderings of the sodium ions in these materials that are often coupled with the electronic ordering of, for example, the manganese 3 and the manganese 4. So I wanted to show you one example of our work, and that's in the phase beta sodium manganese oxide. That's not one of these straightforward layered compounds, it's a zigzag compound. And I just wanted to do this, to show this example, because it illustrates how we attack the sodium NMR of these materials. So why are we looking at it? Well, we were interested in the idea that if you pulled all the sodium out of this material and you had this tendency to shear, well, what would a zigzag type arrangement do on shearing? And so in collaboration with Peter Bruce and his group in St Andrews, now in Oxford, we did a lot of the electrochemistry of these materials, and we showed them, or actually in this case it was Peter's group that took this microscopy and showed that the crystallinity was retained after sodium reinsertion after multiple cycles, but actually when you pulled all the sodium out, the layers sort of tried to move and you got a very highly disordered materials. So just to think about the structure of these materials, we started off by doing sodium NMR of these compounds. So this material has one crystallographic site for sodium, so you would expect only one sodium signal. And instead we got this one major site, but we also got two other sites. These sites have, or these signals are associated with very large shifts. These shifts are called hyperfine shifts, and they come from the transfer of spin density from the manganeses into, in this case, the sodium. So we can think about what might cause these shifts by looking at, again, model compounds. And what we recognized, and Van Tendelu's group in Belgium at the same time published a paper looking at the same thing, was that you could readily form intergrowths between this zigzag structure and the layered phase. And we then synthesized the layered phase, which they had a peak at about 751 ppm, and we could then assign this little minor peak then to an intergrowth of a layered phase within the zigzag phase, and then the shift that was sort of the second most intense was halfway in between the two, and so it made sense that that was clearly the signal of the sodium at the interface between the alpha and the beta domains. Okay, so how do we rationalize the shift? I already told you that there are measures of the hyperfine shift. The other name for it is the Fermi contact shift, and it's a measure of how much spin density is transferred from the paramagnet, in this case the manganese, to the NMR nucleus, here the sodium. There are also three through-space interactions, so dipolar interactions, which adjust the coupling of in this case the sodium, with the local field caused by the manganese, and that in the NMR spectrum gives rise to these things called spinning sidebands, and that comes from the fact that in order to get high resolution NMR, we do magic angle spinning, where we spin the sample at the magic angle, where this is 54.7 degrees to the field, and you get rid of, or you form a time average of these interactions. So over the years, my group has spent a lot of time developing systematic rules to understand these hyperfine shifts. And what we did was to go back and look at the same, or use the same arguments that people use in magnetism to look at coupling between ions. And so we used the Goodenough Kanamori rules to explain why you might have large shifts. If you've got these 90-degree interactions, we have a direct overlap. And if you have shifts that are 180-degree interactions with orbitals of no unpaired electrons, then you got very different mechanisms and negative shifts. And so this is all going back a long time ago, but we worked in 2003 with Gerd Seder and then postdoc Danny Carlier to do some simple spin density calculations of DFT to work out where the electrons went to and why we got these positive and negative shifts. And so this is just a spin polarized DFT calculation where I'm showing you the difference between the up and the positive and the negative spin density. And so in blue is positive spin density, and in black is negative spin density. And this is a calculation for lithium cobalt oxide. So it's a layered material. So here's the lithiums, here's the cobalts. And what we've done is we've substituted in a chromium. And the reason we've done that is chromium 3 plus is D3. It's isoelectronic with manganese 4 plus that we were interested in. And you can clearly see the unpaired electrons sitting in the T2G orbitals that result in positive spin density on the lithium via this overlap with this 2p orbital, and negative spin density being transferred for this 180-degree interaction. And that's then consistent with the NMR spectra that you get, where you have positive shifts and negative shifts. And so just to, for those of you who are interested in where these shifts are coming from, what we did was to spend a lot of time thinking about what caused positive shifts and negative shifts. And there are two different types of mechanisms. The first one is a so-called delocalization mechanism, and that's the straightforward overlap between the half-filled, in this case T2G orbital, with the oxygen 2p orbital that directly transfers unpaired spin density from the T2G to the lithiums. The second mechanism that gives you these negative shifts is called a polarization mechanism, and the reason why it's called a polarization mechanism is that it's got to do with a polarization of the filled so-called oxygen band in the presence of a field. And it comes from the fact that in the absence of a magnetic field, whether it's a local field due to the unpaired electrons, or whether it's an application of the field in the NMR spectrum, you would have essentially identical orbitals for the up electrons and the down electrons. But when you apply a field, you rehybridize them or you mix in excited states, and depending on how you want to talk about it, and those orbitals no longer have to be the same, and you end up transferring spin density. So that was sort of the state of the field a few years ago. What we've done more recently is to go and calculate the hyperfine shift exactly using the crystal code. And so the hyperfine shift is made up of a number of variables that you can just extract, but the key things are the hyperfine coupling constant, which is a measure of the unpaired spin density sitting at the nucleus, and it's multiplied then by the susceptibility, or the time average of the magnetic moment, and that's how you get effectively from a sort of a 0 Kelvin value up to room temperature where we're making these measurements. And so the sort of challenge we have is to calculate the hyperfine coupling constant, which we can get from the crystal code. We do this by assuming that we have a ferromagnetic system at 0 Kelvin, and then what we do is we apply a scaling parameter to take our 0 Kelvin spectra up into the paramagnetic regime. So this scaling parameter is basically the magnetization in the paramagnetic regime divided by the saturation value that you would have at 0 Kelvin. And so we do that by either by using experimental data. So if it's a Curie-Weiss behavior, we can just fit the Curie-Weiss dependence to the experimental measurements of susceptibility, or we can determine the value directly from DFT calculations. And then we can, using either mean field or Monte Carlo approaches. I just want to walk you through some of that. So what we want to do typically is to work out the contributions to the NMR shift from the different pathways. And so this is an example for a lithium iron phosphate material where we're substituting the iron with different paramagnetic ions here, and we're looking at the effect of this on the phosphorus nucleus. And my former postdoc, Derek Middlemas, came up with a very clever way of analyzing the different contributions to the shift, the hyperfine shift from these different pathways. And so what he does is he starts with an all ferromagnetic system, he calculates the hyperfine shift, and then he flips one of the spins, and from the difference between the hyperfine shift of them all up and one down, he can then get the pathway contribution from that one pathway. And this is just sort of the details of the calculations. What we do is we use the same combinations of Hartree-Fock and DFT that are used by magnetism people. So magnetic people typically find that about 35% Hartree-Fock is required to get a reasonable relationship with experimental measurements. So just to sort of those of you not familiar with this area, if you do an all DFT calculation in these systems, then you end up delocalizing the spin too much, and you get a very inaccurate shift. You also, in terms of battery materials, don't get the redox potential right. And so in DFT, you would typically compensate that by putting in a U parameter, like I showed you for the lithium manganese oxide system, which I didn't talk in very great detail about. But for the NMR calculations, at the time where we started this, there was no implementation of U in these hyperfine shift calculation codes. And so what we do instead is use these hybrid codes where we mix a Hartree-Fock combination with a DFT combination. Okay, so we can do all these and get these pathways. And then we need to get the scaling factors to go from 0 Kelvin up to room temperature. So we can do this experimentally. So here's the experimental code, the experimental determination of susceptibility as a function of temperature. You can see it's an interesting material because it's got a very pronounced antiferromagnetic transition quite close to room temperature. And so one of the challenges we have is we can't use a spin-only value because you've got a lot of persistent correlations in the regime where we do NMR, which is about 300 to 400 degrees. So what we can then do is we can do it experimentally, or again we can use hybrid codes, and we can calculate all of the magnetic couplings between the different manganese environments in these compounds. What we did is we did it for the alpha compound where it's layered, we did it for the beta compound where it was zigzagged, and we also made cells where we had intergrowths between the two, and we did similar things. And so when you analyze the shifts, we can then use the hyperfine shift calculations and the scaling parameters, and we can compare the values that we get from hybrid 20 and hybrid 35 with the experimental values and work out where the different contributions to the shifts come from. And so the only thing I want to highlight to you is that this compound had a large shift of 750 ppm, this compound had a smaller shift of 500 ppm, and by looking at the different pathway contributions to the overall shift, you can work out that the large contribution to the shift is coming from the unpaired electron that's sitting in the dz squared orbital that points to the sodium, the so-called P4 pathway that gives you that large shift. And then what we can do is to use our calculations of all of the different magnetic couplings to try and work out what the scaling factors would be in the ordered regions of our compounds, but also at the interfacial regions of the compounds. And so the sort of thing I haven't explained very well is if you want to calculate a stoichiometric material, you can use an experimental measurement of the susceptibility to give you the scaling factor. But if you have a disordered material and you measure the susceptibility of your material, it gives you the average susceptibility of the material. But if you're interested in what the NMR shift is and the local magnetic correlations near defects, or in this case at the interface between two different domains, then you can't get that from a bulk measurement. But what we can do instead is we can calculate the individual magnetic couplings for this region and this region. We then put them in Monte Carlo codes, and we can then extract the magnetic couplings that are relevant as a function of temperature to the disordered regions, and we can use that to calculate the different NMR shifts that we would expect for this region and compare them with experiments, and the agreements are really very good. So these are the experimental values for the beta phase and the alpha phase, and these are the calculations, and they're very close to the experimental values that are sitting down here. So why is this important? Well, then you can go on and you can look at the sodium spectra as a function of state of charge, and you can then work out what happens to the different sodium environments as you pull sodium out of the material. And basically the sort of take-home message from this particular slide is that as you pull sodium out of the material, sodium comes out of the beta environments before the stacking fault sites and the alpha sites. Just to show you that we can go on and we can do different chemistries, we've done exactly the same for magnesium NMR. Magnesium NMR is horrible, but because we can predict where we might expect the signals, we can readily go and look for the NMR signals, and we can calculate, again, so we can use DFT calculators where they are, and then we can find signals that are extremely weak and look for disordered compounds. And so the magnesium-manganese compound has it forms inverse type arrangements, and you can find these if you know where to look for them. Okay, I just wanted to end by telling you one story, and that's to look at oxygen NMR. And so oxygen is a horrible NMR nucleus because the oxygen is 0.037% abundant. It's also, if it's in a paramagnetic material, right next to the paramagnet, and so it's shifted by a very large amount. And so these are some of the first high-resolution oxygen NMR of paramagnetic oxides, and this is in a material with stacking faults where we're using the oxygen NMR to quantify the nature of the stacking faults. The thing I really want to tell you about, and I think I've got 5 minutes left, is to look at some fuel cell materials. So fuel cells, solid oxide fuel cells, operate by moving oxygen through a ceramic membrane. And what you want to do is to try and lower the temperature of the membrane so that you can get to below the sort of 800 to 1000 degrees centigrade that yttrium stabilized zirconia systems work, so that you can particularly reduce cost and deal with issues of stability as you cycle from high temperature to low temperature and degradation of seals and so on. And one thing that's very important is to try and get new, better materials to catalyze the oxygen to O2 minus transfer so that you can lower the temperature. And so people are interested in mixed ionic conductors that allow you to increase the interface between oxygen and the electrolyte so that you have more surface area to do catalysis to allow you to go from O2 to O2 minus, but you need a mixed ionic conductor because the oxygen ions need to get into the electrolyte and you need to get the electrons in to reduce the oxygen to O2 minus. So the oxygen NMR of diamagnetic materials is relatively straightforward. And over the years we've done a lot of oxygen NMR to identify how different oxygen ions move in lattices. And this was just a very nice example of a number of years ago where we looked at this layered compound with tungsten oxide layers shown here and bismuth oxygen layers here. And by looking at the oxygen NMR, you could see that as you heated the material up, you got a collapse of the NMR spectrum from 2 signals to 1. Those 2 signals correspond to the 2 oxygen environments in the layer. And it was just telling you that at about 200 degrees centigrade, you got exchange between those 2 lattices. But that was easy because that was diamagnetic. So when we now move into a paramagnetic regime, we're going to have to deal with the interaction now of the paramagnet with the nearby oxygen, and the spectra are going to become a lot more difficult. So to attack this problem, we looked at this Ruddleston-Popper phase, the lithium nickelate. So this material contains perovskite layers with lanthanum oxide layers in between. And the reason we chose it was that in these lanthanum oxide layers, you have oxygen environments that are only coordinated to lanthanum in the first coordination shell. So they would look diamagnetic. And so we thought we would stand at least a chance of seeing those ones, even if we couldn't see the oxygens in these mixed nickel-2, nickel-3 layers. These compounds had been studied by the Imperial group, and using semi-empirical methods, they proposed a mechanism for migration involving the oxygens in the interstitial layers, where involving a knock-on mechanism when oxygen jumps to an axial environment and pushes it out into the nearby vacancy site. And they got an activation barrier of about 0.51 EVs from that. So we did oxygen NMR of this. We enriched the material with oxygen gas, and we did NMR using a normal way of getting NMR. And when you do that, all you just see is this one signal due to oxygen surrounded by lanthanum. It's got a chemical shift that's very similar to that of lanthanum oxide. So that makes sense. So then the question was, where were these oxygens in the nickel layers that we were much more interested in? In order to find them, we had to change the way we did the NMR. We actually had to step through multiple different frequencies. So each of these broad signals is a spectrum acquired at a different offset. And then we sum them all up to get the overall spectrum. And it's very broad and it's not as beautiful as the spectrum here, but you can still make out 2 different resonances. And by just using simple arguments, you can assign the one that's shifted by 1 amount to the oxygen next to 1 nickel, and the one that has double the shift is the oxygen next to 2 nickels. So we've for the first time identified the oxygens in these paramagnetic perovskite layers. We then did our hybrid DFT calculations, and we were able to make unit cells with oxygen interstitials. And when we did that, we could identify at least 4 different environments that were caused by the oxygen sitting in the interstitial sites and displacing the nearby nickels. And so depending on the degree of displacements, we got shifts from about 390 ppm down to 318. So this was the least displaced environment. And so given the fact that we thought we really had to detect more local environments on these sites due to the presence of this oxygen, we went through and we used some more complex NMR sequences to try and tease out more information from the NMR spectra. We did two things. This is a sequence where you basically get rid of the spinning sidebands, and you can see when you do that clearly that there are at least 4 different local environments. We used another method where we could select the different signals based on the quadrupole coupling constant. That's a measure of the electric field gradient at the nucleus. We can readily calculate quadrupole coupling constants from DFT, and we were able to see that the two environments, this environment versus this environment, had very different quadrupole coupling constants. And so the oxygens in these axially environments here had very small quadrupole coupling constants. The oxygens in the nickel-oxygen-nickel environments had much larger ones, and by using appropriate NMR sequences we could filter between the two and we could assign them. And so what was really interesting was we could resolve the 4 environments that we'd predicted from DFT. Okay, again, you might say, so what? What is this telling you? What we were then able to do is to follow the change of spectra as a function of temperature and look at the dynamics of the nucleus, the oxygen NMR. And so if you start at room temperature, you can see going up to about 130 degrees, you actually lose the oxygen NMR signal. And what this is an indication that the oxygen that's in a diamagnetic environment is starting to exchange with the paramagnetic environment, and it's disappearing. The other thing that's interesting is that this very broad signal actually sharpens up as you get to high temperatures. And the reason for this is coming from the fact that there's an orthorhombic to tetragonal distortion above room temperature. And what we speculate is that the onset of the dynamics of the interstitials exchanging with this axial environment starts to rocking or motion of the octahedra in this perovskite layer that then drives an orthorhombic to tetragonal distortion, which is why you get this much more symmetric environment. And at the same time, you can work out, or you can see directly from the NMR spectra that it's coupled with the oxygen motion. And by analyzing the loss of intensity as a function of temperature, you can actually get the activation barrier for transport, which is remarkably similar to that predicted earlier on from the semi-empirical methods. And so this is just showing you that you go from room temperature from an orthorhombic environment to a tetragonal environment, and that tetragonal distortion, or the lack of the orthorhombic distortion, we believe is due to this motion that's starting on the oxygen sublattice in between the perovskite layers. And so finally, just to show you the sorts of things we can do in my lab, we have laser probes that allow us to go all the way up to 700 degrees or 800 degrees. So this is just showing you the laser heating that's going on. And when you do that, you can take this very broad signal, and it almost completely collapses as you start at high temperatures having motion involving all of the oxygens and all the different environments. So with that, I'll just conclude by saying I hope I've been able to show you a little bit about how we link theory and experiment, originally in the amorphous materials, then through to hyperfine shifts of sodium cations and lithium cathode materials, starting to work in magnesium NMR, and starting for the first time to really get oxygen NMR spectra of paramagnetic materials that are relevant for both batteries and fuel cell materials. And with that, I'm not going to talk about supercapacitors unless someone has any questions. I'm just going to go and conclude my talk. So I just want to thank all the people that have been involved in this. The transition state searching and the PNMR was done by Jan Seymour and Raphael Clement in collaboration, or with Andy Pell when he was still in my lab. Jay did the magnesium NMR, Hee-jung and Phoebe and Josh did the germanium, the tin and the silicon, in collaboration with Peter Bruce, Shirley Mung, Lyndon, who's now at EPFL, David Wales, Andrew Morrison, Chris Pickard, and thank you for listening.
Great. Thank you.